On the last day of February, the next Optica Online industry meeting will explore new applications in the fast-changing world of optical fiber sensors. On our panel of end users, we welcome Siebel, an Archer company. They are specialists in distributed acoustic and temperature sensing in oil and gas. But wait, today there is so much more to fiber sensing than oil and gas. Listen. For the first time, in a fiber sensing online industry meeting, both NASA and ESA will share their preferred future. Our friends Patrick Chang from NASA and Ian Mackenzie from the European Space Agency have been involved in several fiber sensing activities. ESA recently shocked the world by announcing an open tender.
Humans will walk on the moon again.
To make a feasibility study for relevant technologies related to sustainable life on the moon. Does this include fiber sensing on the new moon base? Let's find out. Then we hear from Cambridge Consultants, a company that has enabled many breakthrough medical developments worldwide. And don't let the name confuse you, they are not consultants. Cambridge Consultants are one of the leading high TRL system integrators in our industry. For many years, they have invested in fiber sensing. Why? How can Optica corporate members help them? And in the medical field, Canadian FISO specializes in integrating finest fibers into advanced medical systems. They are known for miniaturized optical pressure sensors, which are down to 200 micrometers in diameter. One of their biggest success stories is the development of the smallest catheter combined with fiber optic technology that actually calibrates in vivo and is commercialized by Getinge. The Optica corporate member who has invested the most in fiber sensing is Luna Innovations. We should ask them about the advanced fiber optics that give early warnings of dynamic changes to levees that protect harbors from the effects of climate change. How can we help them accelerate such a significant development? And to finish strong, we cross to the French company Pixel-sur-Mer, well known in the sailing race universe for designing onboard systems to optimize the navigation and precision structure of the world's fastest racing yachts. As always, the purpose of this meeting is to discover new opportunities for your technology in this sector in photonics. The conversation on fiber sensing begins precisely at 10 a.m. Eastern Time, 4 p.m. here in Central Europe. See you there. Hello, everyone, and welcome. Welcome to the online industry meeting on fiber sensing. Thank you very much for all the companies who have asked us, really asked us to organize a meeting on fiber sensing. Thank you for your feedback, your word, your wish was our command. Helena Diaz-Irriega from Optica, Pamela Robertson from Optica, Elise Fritz-Gage from Optica, and the rest of the corporate engagement team have worked very hard to bring you what we think are some of the key drivers of next generation innovation in fiber sensing. Remember, the purpose of this meeting is to make sure that you find connections, a way for cooperate. So everybody in the room is not a listener or a speaker. Everybody in the room is part of a meeting. All of you should have a chance to say what you can do for others and what can others do for you. I'm going to start. My name is Jose Pozo and I work for Optica. I'm the Chief Technology Officer and my job is to build a global industry association. What we want to do is to make sure that we can help all of you finding ways to accelerate your business, provide you with market data, with events, and with ways to access to hire the talent that you need to fill your open positions. And I have something very big to announce. All of you should have a chance to go to optica.org/market reports. Go there. You will find hundreds of technology and market reports that you can download. All you have to do is basically select what you need and select what you need, put your email address at the bottom, and then welcome to your inbox. Let me just show you how it works. You go to optica.org/market reports. As easy as that.
It goes here, and then you select that you want to have the latest market report on global frequency comms, on displays, on silicon photonics, on 3D image sensing, and at the bottom you put your email address and they come to your inbox. You don't need to remember any password or anything. That's what we want to do to make sure you access the latest market data. I also would like to remind you that this is the a strong force of a committee, a group of companies who are leading the efforts on this industry, Global Industry Association. I would like to acknowledge their support, and of course, our president, Michal Lipson. Thank you very much for the great support that you're doing on building the Optica Global Industry Association. This is our second meeting in the season of offline industry meetings. Today is fiber sensing. Next month, quantum key distribution. We already got confirmation from BT, Verizon, Huawei, Deutsche Telekom. It's going to be spectacular, that meeting. But today is all about fiber sensing. And I have to say I'm overwhelmed by the speakers. We have Sibel, NASA, ESA, Cambridge Consultant, FISO, Luna, and Pixel Surmer. But most important, I'm overwhelmed by the support of the industry. We collected all these companies are registered at the meeting today. They're either following the meeting in the Zoom room or in YouTube. And all of these companies have registered to the meeting because they have something to say at the meeting. We have analyzed what is the business plan for the meeting, what is the role in supply chain. If you want to get in touch with any of the participants today, all you have to do is send me an email and I'll make sure I make the introduction. Please make sure also that after the meeting, there will be a YouTube link for everyone to follow. Please make sure that you share it with your audience to make sure that you would tell people you were there, and especially if you were a speaker, you can share the presentation with them. And this meeting is live streaming in YouTube. So let me say hello to the YouTubers as well. So hello, YouTubers of the world. Thank you very much for being there. If you have any question, please write it in the chat and make sure I read it in the room. It's also valid for the people in the Zoom room. If you have any question, you can write it in the chat, with the only difference that if you have any question, the floor will be given to you because this is a meeting, not a webinar. And with this, I would like to once again thank everyone to have this great meeting. We started on time, we're gonna finish on time. It's a 2-hour meeting, and the first speaker of the meeting today is from a company that we have been engaged very much in the last years. We are talking, of course, about Sibel, one of the leading companies in sensing systems for the oil and gas sector. And we have the honor of having with us Isabel Pellegrini. Isabel, thank you very much for being with us. The floor and the attention of everyone goes to you. Tell us how Optica Network can help you. The floor is yours.
Thank you, Jose. I will just make sure I get my settings right first. There, can everybody see my screen?
Gorilla Glass Clear.
Great. My name is Isabel Pellegrini. I'm working for Sibel, an Archer company. My current job title is a Principal Technical Advisor for distributed fiber optics, and I'm in charge of internal software development, creating new workflows, doing some research on data to prototype workflows. Sibel is in the oil and gas industry, and today I'm going to discuss or explain how we think distributed fiber optic sensing can enable some change. Well, in the oil and gas industry, we like to say that traditional logging using point measurement, that is running electronic tools at the end of a cable, for example, doesn't give you all the information because you can always miss an event. But if you run a distributed fiber optic system, then you just run your fiber along the well to your target depths and just leave the fiber there and start data acquisition. And that gives you all the well, all the time, depth versus time, 2D information, which is much, much more than what a traditional point sensor can give you. A few words about Sibel. So we are an intervention company in oil and gas wells. This means that we deploy our fiber optic using temporary intervention as opposed to installing our fiber permanently, for example, attached to the tubing or to the casing and being cemented in place so-called permanent installation. So we run the fiber, we do the job, and we get out of the well. And we do that through means of our carbon rod, of which you can see a picture there of the trailer in the US. Let me just get the pointer here. Yes. So this is the logging cabin. This is the reel, which is about 3.5 meter in diameter. And you can see the rig up there. The carbon rod is, as its name says, is a carbon composite rod. And we can deploy it either with or without electrical conductors. So it can be pulled down to very deep wells, like typically 23,000 feet. We can run on wireline, or we can run on disposable fiber. The disposable fiber is a clever piece of equipment that you can just drop by gravity in your well. And the fiber is actually coiled inside the dart, and it deploys passively as the dart drops inside the wellbore. We typically do distributed acoustic sensing, distributed temperature sensing, flow profiles, frac monitoring, well integrity. Here, I'm going to talk a little bit of frac hit monitoring. So, for example, here you can see that we have a fiber deployed in a monitor well, and those other wells are wells that are going to be fracked, i.e. the operator is going to inject a lot of hydraulic fluid and sand to crack the formation and enable production. So here you see a gun barrel view. Typically, we have spacings of 1,000 feet, more or less. And what happens is that when they frack, you can actually monitor what's happening inside the monitor well on the fiber optic. And this gives you this kind of image. So if I show a different color, for example, so this is a frac hit. You can see on this axis there, so that's along the well axis that you're seeing here. That enables the operators to get better control of water volumes, of well spacings, and fracture growth. There is a lot of discussion about hydraulic fracturing. I'm not going to go into it, but fiber optic is one of the ways where you can start optimizing the parameters of the hydraulic fracturing. How can distributed fiber optic help elsewhere? So in the oil and gas industry, we have operators who do distributed acoustic sensing, vertical seismic profiles, i.e. they actually use the dust to acquire VSPs to calibrate the surface seismic and get a better understanding of their fields. And I was recently at a workshop where I could hear one of the major companies say, we want to make the most of our existing fields and mature fields before we start developing new fields, which I believe is a great attitude. In terms of well integrity, we are also going towards automated event detection, which means that we can start preventing issues or having early detection and reducing the severities of incidents, for example. Also, we're talking a lot about carbon capture and sequestration, for example, the Quest project in Canada. So this is about permanent monitoring, so permanently installed fiber that would be used during the injection of CO2 and to monitor after the injection. So you can use passive microseismic, you can check how your plume is evolving versus time. And this is 24/7 automated event detection, and saves you the need to drill a well that is specially equipped with geophones. And the nice picture on the right here, it is not dust data, it is surface seismic, but the principle is the same. In Sleipner, which is a Norwegian field, they've started injecting CO2, and you can see that with time lapse for the seismic, they've been able to monitor how the CO2 plume is growing, and you can see the difference on the images there. And this is either depth or two-way time, and gives you an image of the surface and ensuring that the plume is controlled. The challenges, so one of the main challenges, obviously, for detection is the signal-to-noise ratio. And so we have those long horizontal wells, which have a laminar flow at the bottom, and it's very difficult to detect. And also a question about the leak detection threshold. And if you look at the picture on the right, that's a typical example. So I'm used to looking at those things, and if I tell you that there is something rising, you're not necessarily going to see it. It's very hard to see. And it's the same actually for the machines that we are using to model. We need to have a sufficient signal-to-noise ratio to be able to detect those events, and this is critical for automation. There is also the acceptance, so it's a little bit like electrical cars. Like in Norway, for example, we had 80% of new vehicles that were actually electric. But if you take the rest of the world, then the numbers are not that high. And it's the same in the oil companies. So you get groups that are typically research and development, where you find big acceptance of distributed fiber optic, while the rest of the company is still a little bit behind. So yes, modeling signal-to-noise ratio, acceptance, costs, etc. So those are the challenges, but we are getting there, because at workshop nowadays we find operators actually selling us fiber optic, like to the service company, and telling us how much they love it and showing us their results. When 10 years ago, it was actually the service companies trying to do that for the operators. So that's it for me. I'm a little bit over time. Thank you very much.
Thank you very much for a great presentation, Isabel. It is great to have you here, and it is great that you came here to show your challenges. And they are signal-to-noise ratio, they are three-phase flow, they are modeling of superficial CO2 injection reference, acceptance, cost, and automation of machine learning. The floor is open for questions. We have a few for you. Let me start with the Optica staff. Tom Hausken, all the way from Silicon Valley, all the way from California. Tom, what do you have in mind?
Well, I was just curious, first of all, if that carbon rod is rigid or if it's flexible like fiber. But I guess you also just mentioned that there's an acceptance issue, and I guess I'm wondering, so this is versus using just thumping the ground from the surface, or you mean using a particular type of distributed sensing?
So the carbon rod is a semi-rigid type of cable. So it's about 0.6 inches in diameter, and it contains a fiber encapsulated in a metal tube, or several fibers rather. And when you hold it with your hands, it's unlikely that you're going to be able to flex it. But over long distances, it's actually flexible, and it can actually coil in the well, and you can coil it, as you can see on the drum. In terms of acceptance, I'm referring to, compared to normal electronic tools that you typically use to acquire measurements. So one of the issues we've had initially with fiber optic is we could see a lot of things, but what are we actually seeing? And so it was a bit difficult to explain that at the beginning, because we could see all those fancy pictures, and then it was a bit difficult to understand, the transfer functions, what cause was creating what effect. But we made a lot of progress with that. And we fairly understand well now how to interpret the data, except, for example, three-phase flow, which is kind of still the growl. Yes. Does that answer your question?
But when you say the traditional method, are you referring to where you thump the surface and then look at the reflections coming back from the surface?
Okay, you're talking about seismic. Yes. So
yeah, that's traditional.
So yes, so the example I was showing you was time-lapse seismic from from surface seismic. So yes, so you're talking, for example, boats with streamers and yes, and so geophones at surface, for example. Now we are talking about using the fiber optic as sensors, as geophones. So it's a little bit different, but one of the advantages of this is that you actually get twice the frequency resolution compared to the surface seismic.
Thank you very much, Isabel. We have more questions for you. The second one is coming from the company FiberCore. FiberCore is a special manufacturer of specialty optical fiber, and they are represented in the room by Andy Gilloley. Andy, what do you have in mind?
Hey there. Thank you very much for your presentation. So you mentioned the signal-to-noise ratio, of course, always a big problem for long-range measurements. Have you looked into the enhanced fibers like the EDAS fiber, which improves the signal-to-noise ratio for DAS?
Yes. So for subsea applications, there are various ways of enhancing the signal-to-noise, and engineered fiber is one of them. And enhanced fiber, engineered fiber is one of them. Yes, and you can also use circulators, and yes, there are a lot of techniques to improve the signal-to-noise ratio. But still, yes, you can still do better. And so definitely, if you're trying to detect a leak at a stage where it's as small as possible, there is always room for improvement.
FiberCore is one of the key manufacturers on specialty fiber, also of EDAS fiber. I recommend everyone in the room to actually check their catalog, different fibers that they can actually manufacture. Thank you very much for being with us, Sandy. I'm going to come back to you later. We continue, and the second company that wants something to add to the meeting is Subcom. Is representing the meeting by Sanjay Khatri. Sanjay, what do you have in mind? What question do you have for Sibyl?
Hi, thank you. Maybe I missed this, but some of the sensing you're doing, was it terrestrial or offshore? And if so, how long of links are you looking at? Like, how long are these links that you're investigating, sensing?
Yes, so typically we operate on land wells, but we've also done some offshore work. So it's just intervention, and the longest wells that we've been into were about 23,000 feet. That's about 6,000 meters.
Okay.
Thank you very much. And the next question comes from the market leader of specialty optical fiber, OFS, Steve Allen. Steve, what do you have in mind?
Well, basically, I was asking the same question Andy asked. Type of fiber, what is Zybel doing for longer lengths? Are you combining enhanced fibers and standard fibers, that type of thing?
So we don't operate subsea, and typically you would find this kind of engineered fiber for subsea applications where you can have several kilometers of umbilical that reduce your signal. And as far as I know, typically the umbilicals are standard fiber, and then you would have your engineered fiber or enhanced fiber inside the well.
The last question in the room comes from Ahmad Atieh from OptiWave. Ahmad, please tell us, what do you have in mind?
Thanks, Jose. Nice presentation, Isabel. So I'm just asking about the transmit and receiver side, actually, in your case. What would be like what you are using for the system? And because one issue is you are talking about the signal-to-noise ratio, how is the modulation or the wavelengths or all these things would affect that? Okay, so typically we are using distributed acoustic sensing and distributed temperature sensing systems, and so we just pulse the laser from surface, and well, in terms of the electronics of the system itself,
I know the DTS is usually single wavelength, and the DAS are depending on the systems. Some systems are using several wavelengths, or some others are just using a single wavelength.
Thank you very much, Isabel, and thank you all the fantastic participants in the first Q&A. Let's continue with the program because we really had to finish on time. The next two presentations are key for the success of this meeting. We have NASA and ESA back to back, and they are here with a set of wish list, dreams. So let's start with NASA, and let's welcome to the stage for the first time and at one of our online industry meetings, Patrick Chang. Patrick, thank you very much for being with us. The floor and the attention of our Optica community goes to NASA, goes to you.
Good morning, everyone. Thank you for attending this talk. And I'm here to talk about what we have been doing in terms of fiber optic sensing system at NASA Armstrong Flight Research Center out in Edwards, California. And see, I'm gonna share my slide deck here. So everyone can see my slide, I assume?
Yes, we can.
Great. So just a quick table of content, what we do here. We use fiber Bragg grading to do sensing. And we talk about how the NASA unique technology of OFDR, optical frequency domain refractometry, the reason we use it, and some of the technology we implemented onto aeronautics flight and space flight. So why do you choose fiber optic sensor over strain gauge, resistive gauge? So in terms of fiber, you can pack hundreds, if not thousands, of fiber Bragg grading onto a small size fiber. And in terms of implementation, and in terms of size advantage, there's a lot of advantage using fiber optic for structural health monitoring as opposed to traditional strain gauge to monitor strain on aero structures. Since we're in Optica, everyone, I assume you guys know fiber Bragg grading is basically a reflective gauge, and we look at the environmental change due to either temperature or strain changes, and then you get that wavelength change, and by measuring the wavelength change over the initial wavelength, we'll get either the strain or the temperature change on the environment. And I'm just gonna go really fast. So strain change kind of like an accordion, and that's how we do it. Traditional way of using fiber Bragg grading, where it's prevalent on the industry, is using a technology called wavelength division multiplexing. While broadband light source, each of the fiber Bragg gradings is individually coded, has an individual wavelength, and the advantage is easy to use, but then the disadvantage, you can only have a certain amount of fiber Bragg grading onto a strand of fiber, so limited by your bandwidth. But using all and this is the disadvantage of the WDM technology. When two gradings is close to one another, then you have that aliasing effect. So in order to mitigate that, your bandwidth limited. So from NASA uniqueness, we use optical frequency domain refractometry. So each of the gradings is having the same wavelength, have low reflectivity, and then we use signal processing in order to get that grading out. I only have 7 minutes, so I'm gonna rush through this really quick. Advantage. So now you have FEM type of structural health monitoring onto your critical structure, be it for flight or for space application. Then you would have that half-inch high spatial density that you would need for critical structures, such as this composite crew module that we have the test on. So how does OFDR works? I mentioned that each of the gratings, it has the same wavelength, and the only differentiator is where the grating is relative to your starting point, and then by this length difference, we can translate that into frequency domain. Layman's term, it's basically tuning your favorite radio station. You have multiple frequencies, and then you basically your receiver the frequency, and you tune one at a time. Same thing as OFDR. You have a laser, and then we basically will dial into one individual grading, and then look at the wavelength change, and then we'll move on to the next one. So as you can see, there's a lot of computational work in terms of doing all the FFT and inverse FFT together. These are typical fast component that we do. We like to call that as an instrumentation suite. You have the laser, swept source laser, fiber integrated into structures, and this is kind of like our current capability. We have systems suitable for ground testing for our various aircraft here at Armstrong. We also recently work with a partner in the space side of the house, and we developed a launch system that we use to monitor a space launch system. So what's our role? We basically this technology was developed late 90s at Langley Research, and we improved the algorithm and improved the electronics, and then we ruggedized the system and package it and so such that we can do a lot of structural health monitoring, such as strain. I talk about that, and then the absolute units temperature and cryogenic liquid level. And then other fields that's relevant to space launch community. This is one of the example that we have done. Is a complete Orion crew module 1-to-1 representation, but this is a engineering design using all composite material, and we use the fiber to validate testing. So you can see that when the composite crew module is under load, you can see the strain distribution while it's under load. So it's really helpful for the FEM design to figure out what's going on. Secondly, this is also one of the interests in the space side of the house. You want to measure the cryogenic liquid level, or the temperature stratification of between the cryogen and the Ullage level. And fiber, because it has that high spatial density, it become a good candidate to do that type of monitoring. And lastly, we can do structural health monitoring in situ in terms of putting the fiber onto aircraft. This is the Icona, NASA's version of the Predator 2 aircraft. And we have publication around. So if you want to research more, I'm just gonna fly through all these slides. And this representation, now once you have string, you can actually get the real-time structure shape, because we know intimately the shape of the aircraft, and then from the string we can actually get shape. And finally, our technology has been flown to space, which is the LAFTE project at launch last November. And we were invited to put onto fiber to put on the nose cone of such vehicle to monitor the reentry heat distribution, and they've proven to be valuable. So I'm gonna skip the video for the sake of time. And so in terms of summary, so what sort of challenge the NASA community will see for this system is adaptability, because on NASA we have something called a technology readiness level, which means that how this technology would be helpful to apply to different NASA technology. We will need to have shown that this technology is mature enough to be applied for critical vehicle monitoring equipment, and so we will probably need to proven ourselves in order to do that. And also in terms of just the hardware, because what we do OFDR wise, there is a critical need for a single launch tunable mode swept source laser that's robust enough for aeronautics and space operation. And we are always looking for a fast tune laser to satisfy our unique criteria. So that's one of our challenge. And the second, just more general term in terms of challenge, is the is how the industry would see this optical sensing. How would they apply this sensing to different fields beyond aerospace application? With that, I thank everyone's attention, and I'm looking forward for your questions.
Thank you, Patrick. We have any questions here from the audience? Okay. So in terms of, Patrick, some of the changes that you've had between 2002 to 2000, well, up to 2022 is a reduction in weight. What do you foresee, I guess, moving forward with, or is that even?
We do have a road plan of using. We have an interrogator suite that would rely more on the commercial side. Right now we use a custom FPGA to do most of the signal processing. We are moving on to a commercial over-the-counter system that stem from the smartphone industry. So we're looking forward to further miniaturization on that front. And we have been working with some of the industry partners to develop a swept source laser that would be able to specially specially tailored to the aerospace industry.
Excellent. Well, thank you so much. And I think in terms of time, thank you for joining us today, Patrick. I really appreciate it.
Can I say something here, Patrick?
Yes.
It is really fantastic that you told us about miniaturization. As you know, one of the biggest focus points of this association is the manufacturing of photonic integrated circuits for large scale. And many companies, and actually one of them in the room, has manufactured integrated photonics-based interrogators for string sensors, FPG based. Patrick, do you have any experience with interrogators from companies like Optics 11 or Technovis, now Photon First?
We have worked a lot in terms of the unique specialty fiber production. We have worked with FPGS, and we have worked with OFS and many other companies here. Fiber core, actually, also we have worked with in terms of interrogator and specialty fibers. So yeah, I have worked with a lot of people in this.
Our
talk.
friend Bram Van Ho is in the room. So hey Bram, good to see you. But I want to give the floor to the company Optics 11 FAS. Selvan Ibrahim. Selvan, are you in the room with us?
Yes.
What do you have in mind? This looks like a great opportunity for cooperation.
Yeah, so thank you. It's a very interesting talk. I have one question in terms of the performance of the interrogator. What is the maximum speed, the sampling speed, and what is the wavelength accuracy that you have for measuring FPGs?
We in terms of speed, we're limited by the speed of the swept source laser that can sweep And right now we can depend on the strain range or the wavelength range that we want to monitor. We're limited to at most, let's say 100 Hertz. And the wavelength accuracy is based on strain. So usually to convert to strain, we'll have a plus or minus 5 microstrain.
Okay. And for the laser you're looking for, what type of line width you're interested in?
We are doing for external cavity laser swept source, we're usually looking at 1 megahertz or lower.
Okay. And have you considered, as Jose mentioned, photonic integrated circuits for the system?
We did. We in terms of miniaturization, in terms of multiple channels output, we had tackled with research on photonic integrated circuits. Also, the specialty and then the low volume that we are looking for. It's we walked on that path before.
Okay.
And what was the result? You worked on the path, and what is the current TRL for integrated photonics interrogators in NASA?
And we dabble on 2D PIC design, and the result wasn't as good as the bulk fiber optics result. So we.
Patrick, 4, 5, or 6? What is the TRL for peaks in space?
I'm sorry?
What is the TRL for peaks in space? 4, 5, or 6?
I'm sorry, I didn't understand
the technology
question.
Readiness level. The technology readiness
right
level
now,
for NASA in peaks
TRL, with the lofted flight, we are currently at 6. We do have a system that pass all the tests on the shelf. It has a TRL of 9.
Fantastic. Selvan, you had to follow up with Patrick.
Yeah.
And also my friends from FBGS also in the room. Bram, you had to follow up as well. Patrick, there is somebody else who wants to ask you a question. This person is John Angus from River City Group. John, what do you have in mind?
Yes, Patrick, I have a couple of questions around the sweep source that you mentioned. What sweep range are you looking for in your sweep source?
We're looking for, in terms of strain, if we want to do plus or minus 8,000 microstrain, we're looking usually 10 nanometers of swept source. Usually the most extreme we're looking for is 20 nanometers of continuous sweeps.
And what kind of sweep rate are you looking for? Is this a fast sweep or a slow scan, or what's required for your algorithms and your sensors to work properly?
Usually in terms of swept range, we're looking for 1,000. If it's 10 nanometer of sweep range, we're looking for 1,000 nanometer per second in terms of sweep range.
And do you have a required output power?
Probably what the maximum output usually is 10 milliwatt.
And is this in the what frequency range are you looking at? Is it 1500 nanometer range, or is it the 1300 nanometer range? Or
it's 1550. We're using on C-band 1550.
Got it. Okay.
Thanks,
Thank
John.
you very much. I have a lot of background in this area, so I wanted to understand some specifics. Thank you. I appreciate it.
Thank you.
I appreciate the question, John. So I can't compete with the exuberance of Jose, but I'll try. Thank you, Patrick, for joining us. Thank you for that talk. That was great. And thank you, everybody, for joining us. So I'd like to invite our next speaker up here. We have Ian McKenzie. He's a senior engineer at the European Space Agency. He's also in the Netherlands with Jose. So yes, those two are together. He is going to discuss the fiber optics components for space applications, including the optical communication, onboard signal processing, fiber optic sensing, and optopyrotechnics. Okay, I would like to know what optopyrotechnics are. So Ian, I know that's probably not part of your talk today, but please go ahead, and we look forward to hearing your talk. So it's up to you.
Sorry, I just have to share.
Oh, Thank you. And yeah, if anybody has any questions, just please put things in the chat. And then or raise your hand. I'll just got to make sure that I'm watching everybody out here. Okay, thank you, Ian. Perfect.
Okay. Is that working now?
Presentation mode. There you go. You're all set up.
Okay, so thank you for the introduction. Yes, my name is Ian McKenzie, and I've been working at ESA, the European Space Agency, in the optoelectronics section for the last 20 years, and have been involved in fiber optic sensing for that time. So is fiber optic sensors, is this the right technology for space? And I would say yes. And the reason why is that fiber optic sensors are already in space. We look at the most successful one, it's probably the fiber optic gyro, and companies like XBlue, now Exhale, have 20 years of flight heritage flying these fiber optic sensors. And this involves a large length of fiber. So, the issues of radiation hardness of both that and the source based on an erbium fiber have been, solutions have been found. We also have at ESA flown on Proba 2 a fiber sensor demonstrator where we flew fiber Bragg gratings, and we now have over 10 years of flight data from that experiment, which show again that these types of sensors can be flown in space, do work. In this particular example, fiber optic sensors were used for monitoring temperature and also pressure on a propulsion system. This is a cold gas propulsion system. So basically you release cold gas, which you heat up and then release into the atmosphere to provide propulsion. So this was a propulsion system used on Proba 2. And in addition, I just also mention Lumia, which is something very new. It's just recently arrived on the International Space Station. This is a radiation dosimeter, which uses radiation-induced attenuation as a means of measuring total ionizing doses, which is, a new approach to making this measurement. So let's go on and have a look at a few applications. So the first one, like even before you get to space, there's a lot of testing that has to be done on a satellite. And if we look at a large telecom satellite, for instance, typically you will have over 400 thermocouples applied to the satellite. And these are used during the kind of thermal testing, thermal vacuum testing. This is a lot of, sorry, did I go there? This requires a lot of AIT effort to attach these sensors, and then they all have to be removed again. So the question is, why can't we have sensors on there, particularly if you have lightweight sensors that can be used to monitor the satellite and then used in flight as well? Because in addition to those 400 thermocouples, which have to be removed, you also have the 400 thermistors that are typically used, in flight. So why can't we find a way of using a kind of fiber optic sensing measurement? And so we've been looking at this for quite a while. We still haven't been able to convince the large space integrators that this is the best way to go. But I believe that once we address the issues of TRL and cost, then this could be certainly an interesting option for fiber optic sensing. Beyond this, there's a lot of mechanical testing that is conducted on these satellites, and typically on a large telecom satellite, you might have up to 250 three-axis accelerometers. So the question is, can fiber optic sensing be used there? Or can you use strain measurement to infer acceleration in some way? And so these are questions. We've looked at the numbers, and in terms of the 400 thermistors, if we were to use distributed Bragg gratings or Bragg gratings, but multiplexed together, we could come up with a 50% mass reduction for a flight harness. And also, we'd be very interested in looking at the kind of AIT reduction that's possible with this sort of integration. But if you're looking simply at ground testing, then of course you don't need to qualify for space. So The ground testing, is a kind of low-hanging fruit that maybe is interesting to pursue as a starting point. So next, well, as we go forward, Europe is starting to look at reusable launch vehicles. I mean, SpaceX has shown that this is the best and most commercial way to go forward. And so in order to guarantee European access to space, I think Ariane is already looking at the next generation launcher, which will be a reusable launch vehicle. And clearly, when you start looking at reusability, elements such as structural health monitoring becomes very interesting. And here we see that, this in combined with the increased use of lightweight composites, that fiber optics could certainly offer some very interesting measurement capabilities in terms of sensing. There's also on structures like a large launch vehicle, understanding the flight dynamics is really important. So being able to measure the distortion of the tube as during flight is something that is really interesting to pursue. So, these obviously have severe challenges to fly fiber optics in such a harsh environment. I mean, typically, you're talking about 50 G RMS random vibrations. You're talking about shocks in the order of several thousand Gs. And clearly, if you're looking at re-entry and cryogenic propellants, then you're talking about very extreme environments going from, the hot of re-entry to the cryo environments that you see during the filling of these tanks. So there are several challenges to be looked at, but certainly it would seem that fiber optics could offer very interesting solutions in terms of structural health monitoring of reusable launch vehicles. Now, Jose mentioned the moon, so I guess I have to say something about the moon. Well, I think that at ESA there have been several studies looking at the possibility of using distributed fiber optic sensing as a means to do lunar seismology. And of course, the interest there is to study the dynamics of the interior of the moon, measuring things such as moonquakes, meteorite impacts, and also, the use of mortars to initiate, as a seismic source. So I think that there's certainly a lot of interest, but clearly there would be a lot of challenges with such an approach. Power consumption being one, data processing, how to simplify the data processing of a distributed sensing solution, and how to develop a fiber cable that would be able to couple efficiently between the moon's surface and the optical fiber inside it. So I think this is an area that that we need to do a lot of further research and development, but over the next 20 years, there will be many opportunities to fly such a payload. And I think it's certainly something worth looking at and would be really exciting to be involved in. So the challenges, I mean, looking beyond the success of the fiber optic gyros, which we know have been successfully flown for over 20 years, I think, the main question is how to get the balance to tip in favor of using fiber optics. And in the case of FOGs, it was performance. They replaced mechanical gyros because they were more reliable. But for other types of sensors, you have to find that tipping point. Is it lower mass? Is it being able to have more sensors? Is it immunity to electromagnetic interference? But that has to come, has to give you a positive balance against some of the other challenges which we spoke about already: lower TRL, higher cost, the fact that maybe you need sensor calibration over a 10-year lifetime, and the fact that currently today many satellite integrators don't have the experience of using fiber optics. And of course, cross sensitivity, a critical one when you're looking at technologies like Bragg gradients, where temperature and strain might be a problem. So I think in my opinion, we need to target applications where you need more sensors, where a higher density of sensors are required. I think it's important to look at the early introduction of sensors, when you can look at the full life cycle of a structure, for instance. And, the example on here of what we call the photonically wired panel with embedded temperature sensors. We spoke a little bit about photonic integration, and I believe strongly that photonic integration is a disruptive technology for space because it allows us to qualify technology for space much more cheaply. There is the point that sometimes we give up on performance, but that can be a trade-off. And then finally, I think distributed sensing and the fact that we are now looking at a time when you can have very high spatial resolution distributed sensing, it suddenly becomes very interesting for the kind of structures that we're talking about, which are typically smaller. We're talking about having centimeter resolution rather than meter resolution required. So I think these are the areas that we would like to look at more closely. And with that, I finish, and I leave a few links for you to follow if you get this presentation, so that you can connect with us and understand how to work together with us. So thank you.
Thank you very much, Ian. Ian and me are lucky to live in one of the most beautiful areas in Europe and the world, which is the area between Noordwijk and The Hague. And I'm really happy to have you as a neighbor, John. So, Ian, let me address a couple of points that you discussed during the presentation. First, you said about the need to embed the fiber into lightweight composites. Is there any particular experience that ESA has to that respect?
Yes, we are currently working on a project together with a Belgian company, Common Sense. I don't know, you might be familiar, a small company.
Yes.
And they work together with a composite manufacturing company to embed fiber optic sensors into composites, in particular looking at tank structures. So yeah, I mean, this is an area where we're very interested to explore how we can make use of fiber optic sensing. They use Bragg gratings typically, but yeah, I'm curious, whether high spatial resolution Rayleigh scattering techniques might be equally interesting in the future.
When it comes to that kind of request, normally I go to our key Optica corporate member there, which is Luna. Craig, welcome to the online industry meeting on fiber sensing. I was hoping I could say that soon. Craig, please tell us, what is the experience that you have from Luna on embedding fibers into composites?
Yeah, sure. Thanks, Jose. Ian, great presentation. Thank you for sharing. Yeah, when it comes to composites, we've certainly had some projects where we've done that successfully in a variety of applications, some in aerospace, some in automotive, as a couple of industrial examples. There's just a number of ways that can be done in the production level, and different diameters of fibers to get the measurement coatings, for example, that absorbed into the resin system within the ply layer of the composite itself. So yeah, I'd be curious to know a little bit more about what some of your challenges have been and what some of your...
I think the biggest challenge is entry and exit.
Yes.
So I mean, if you've got a good solution for that, we're all ears. Because I mean
So of course that's always a challenge, and for parts that are laid up where you can control the edge processing a little more carefully, there's ways certainly to create a transition. We've done some designs in the past and have used some 3D printed transition pieces that can help exit the fiber out of the edge base of the part and then transition into a sort of a fabricated assembly for handling purposes. I'd be happy to share some things with you offline on that.
Greg, I hope you're enjoying this meeting with ESA and NASA. Let me bring somebody else that you were not expecting. CERN, Kesivan Kandemir. What brought CERN to a fiber sensing meeting?
Good afternoon, everyone. We are also working with strain sensing at CERN. optical fibers and sensing. And yeah, thank you, Ian, for your presentation. It was very interesting. We are also interested to perform distributed strain sensing in space. But so for now, we are still in the beginning of the project, looking for new interrogators and also the fibers that we would use for this project. So I don't know for now if you have already something advanced in that topic for distributed sensing, because I have not seen if any OFDR could have been used in space, or I know that FBG, yes, I have seen many interrogators, but for OFDR, I don't know yet.
I think you have a good point. So far, we haven't done any work towards trying to increase the TRL of a distributed sensing technology for space. I think the NASA presentation, they were speaking about some approaches where they've increased the TRL. We are currently working with a small UK company looking at, actually it's a French and UK kind of consortium, where they're looking at integrated photonics platforms for doing distributed sensing. And I think this could be a really interesting approach if, you know, because one of the big challenges, of course, is if you have a big complicated optical setup is, you know, qualifying for space, because each component has to be qualified individually. And so if you can integrate a large number of components, you can really leverage on the cost of that qualification.
You know, Ian, I used to do fiber sensing like 20 years ago, and I had a micron optics, sorry, Luna, I had a micron optics interrogator, and I dropped it and I put it back on the table and it still worked. So I think sometimes iterative photonics we are pushing into some kind of direction that maybe there is no need for that. But that's a debate for another session.
Jose, that might be the case, that it will work, but you still have to qualify it, and it's the cost of that qualification which sometimes is prohibitive. And if you can integrate a large number of components, then you can take advantage of that and reduce the cost of qualification. So I'm not saying the individual components aren't qualifiable. I'm just saying that if you have a large number of different components, it could be a challenge to qualify it.
Ian, there is somebody in the room that I want you to meet again, because I know you know each other. Bran from FBGS. Could you comment on your experience of integrating fiber and composites?
Of course, thank you, Jose. Indeed, we have been doing quite a bit of work also with ESA and within different projects. So indeed, we also have quite extensive experience in combining optical fibers with composite materials. And as already discussed before, the biggest challenge is indeed the in and egress of the optical fiber, which is the most challenging part typically. Several new technologies are basically being developed there, also together with ESA, as Ian, of course, knows very well. For example, using self-written waveguides or self-guiding principles to basically guide the light at the ingress and egress point of the composite material to create an optical bridge without having to add an external connector. So that's basically removing the need for an external alignment procedure and having kind of a self-written waveguide structure to make the interconnection between the composite material and the outside connecting backbone then. So there are quite a lot of things moving there. But I agree, it's the most fundamental or the most challenging part to resolve still. Yes.
Bram, I'm going to come back to you later after the presentation, the last presentation from Pixel sur Mer, where they're putting the fiber in boats, because I want to talk about the fiber that you manufacture in particular then. Ian, always a pleasure. Thank you very much for being with us. Let's continue with the program. And now we go to a company that means the world to me when it comes to bringing the photonics to the medical market. One of the companies have manufactured many of medical devices that you see in clinics and hospitals, Cambridge Consultants. And with us, we have Tom Watson, the head of Photonics Innovation. Tom, thank you very much for joining us from the UK. The floor and the attention of everyone goes to Cambridge Consultants, goes to you.
Thanks, Jose. Good morning and good afternoon, everybody. Let me just get on sharing my screen. There we go. Thank you very much for that introduction. I'm going to give you a short introduction to who Cambridge Consultants are. As Jose mentioned in the introduction, consultants is a bit of a misleading term. And on that note, I have a nice cheesy marketing sentence to read to you. that we are trusted by the ambitious to conceive and develop truly original products and services to redefine markets and stand out from the competition. Now, what I want to say is how we interact with everybody in this community. We're not end users, and we are not suppliers, but we simply don't just connect end users to suppliers. We want to do that in innovative ways. We will often ask for things that are outside current specification of products, of devices, and work with you as suppliers and with the end user's application in mind to build the best system that's going to work for them, that enables them to differentiate from their competition in a commercial sense, or actually perform their function if they are on tech cutting edge in DNS space, for example. Who have we worked with previously? So these are some of our previous clients that we could disclose we've worked with. And our model is to become their trusted innovation partner. So most of our business is recurrent business, and we do repeated innovative projects for them to really push their technology forward. So we have lots of trusted partners that are across a number of range of industries. So thanks, Jose, for mentioning that we do a lot of medical work, but the medical work is a third of our business, and the rest of the business is in industrial, consumer, agri-tech, environmental monitoring, DNS, wireless and digital services as well. So we're across the board. We are more than 800 people worldwide, primarily based in Cambridge, UK, but also in Boston, in the US. We've got many laboratories and testing facilities on site. We do a huge number of projects per year. We also have sales offices and representatives in different parts of the globe. So we really do have a global presence in both support and our clients. We've been going for 60 plus years as well. We were one of the original kind of spin-outs from Cambridge University, first on the Science Park. So when they talk about Cambridge as being Silicon Fen, we were very early in that development. We actually span out Cambridge Silicon Radio from Cambridge Consultants, if anybody knows CSR. This is just going to a big matrix picture of the experience and capabilities that we have distributed among those 800 plus engineers. And the reason we have so many of these capabilities is we really take an application focused view on developing products. What really makes their product differentiating, how to translate that into a requirement set, and then how does that link with technology innovation. And whilst we have experts like myself in tech focus, such as optics, we also have human factors engineers and regulatory experts to help build the complete system and how to go about properly managing your product development. Along with these kind of person by person capabilities and skill sets, we also had a load of processes and procedures in place that enables us to do like 13485 medical device development, as well as other kind of documentation and regulatory procedures. We have a long history of using optics and developing products that involve optics for industrial, medical, defense, and consumer, really across the board. This is just a small sample of pictures that I can show you of some of the products we've developed. We've done a lot of life science instruments for diagnostic device and research use life science equipment, which is obviously very high-end optics. At the other end of the spectrum, we've done a lot of work with low-cost optical assays and diagnostic sensors, hyperspectral imaging and advanced image sensors, fluorescence and spectroscopy. We've done a lot historically on micro-optic and optomechanical assembly at that level. We've increasingly been doing a lot of work in optofluidics and the interface between fluidics and optics, which is very complicated because of price differentials between fluidic and optical components. Interferometry, fiber optic sensing, as per this talk, sensors for extreme environments, and recently, and I've been mentioned a couple of times, we're very interested in integrated photonics and its growth, projected growth over the next few years in a variety of different applications. Okay, moving on to quickly talk to you about a project that I'm allowed to talk to you about. So as you can imagine, I can't tell you any details of the majority of the project. So this is a single example which I can talk about, and it's again continuing on the theme of today at the moment, which is distributed sensing. In the sense as the geophone. So it, unlike Isabella, this is for subsea, and due to the poor SNR that you typically get, what we had to do is design a system that enabled high SNR at long ranges. So we worked with a supplier who developed a custom fiber, and these are FPGs in this fiber, and we designed the transducer here, and this is to change axial compression into kind of an XY coordinate, and there were 6 of these transducers in each of this assembly, and this allowed us to an extremely sensitive geophone for subsea seismic monitoring at extreme temperatures and pressures to last 20+ years lifetime. So I really like this example of how we work with this community and with our clients. The clients come with a specification of what they want to achieve. We have an idea of how to implement it, or the fundamental technology to how to implement it, but we have a look around and there's nothing off the shelf that we can just take and use. So we work with, okay, what is available right now? Can we take a step further in terms of the fiber optic technology, the fundamental fiber optic, which in this case, I believe, was having a very thin cladding. And then we design around that. So we make the transducer to loop a lot of fibers, and then that it can easily scale with sensitivity by just a longer loop of fiber. So I really like that example of how we interact with community. So what do I see, or what kind of flavor or taste can I give you of what needs that we've seen at Cambridge Consultants? And I would like to kind of just make a point that whilst I guess high-end sensors are required for industrial or DNS aerospace, as we've had presentations on previously in the meeting, I think there's also a need for reasonably customizable, but specifically low cost, high volume fiber sensors for disposable medical devices. And I think we're going to be talked about a catheter next, which is appropriate. But I also describe fiber sensors as basically anything that's not a fiber for communications. So also like coherent fiber bundles and other things to do like endoscopy and flexible endoscopy, and other things like that. And it's and also for agritech, for large scale installations of monitoring for agritech, right? They've got huge networks, and they can't finance like huge big systems where each of these fibers is expensive. So whilst we should be thinking about how to translate the high-end sensors that we have into miniaturized form factors that can go in aerospace, we should also be thinking about how to make lower cost and scalable solutions. The issue with kind of medical devices, particularly in other things, is that they usually have to be customized to their specific application. So sometimes it's hard to take a generic sensor that you've designed, and then just take that exact thing and put it in a system. That usually requires some tweaking and altering to meet the specification. So. And that's my last slide. I believe I was within time, but I'm not sure.
Thank you, Tom. That was perfect. Okay, so we still have need some questions here. Come on, Jose. I think Jose can bounce in here.
Can Cambridge Consultants help the corporate members with FDA approval of fiber sensors in medical market?
Yes. But the main question is it the right thing for the medical market? And we can help you with both. We can help you understand whether it's the correct market for you, and then how to navigate through it if that's the answer. Yeah.
Eric Pinet from FISO Resonate. You're going to be the next speaker, but I think you need to be part of this conversation now. Eric, what is the current status, the current process to bring any kind of fibered sensor to medical?
Actually, presently there are several applications where we do have already some disposable sensors. And as Tom said, those sensors has to be customized for every single application and every single customers. And not only the sensor, but also the signal conditioner itself, because the signal conditioner has to be integrated in their own device. And so usually we have to do some research and development to fit the best application and the best sensor and the best signal conditioner all together. So yes, it's a long process. Sometimes it takes years, especially due to the approval. But once this work has been done, it's a repeated business, because once the device is approved, it is sold every year with a known quantities. So it's a good but difficult market to go. Yeah.
Eric, Tom, in other application fields, I have interacted with Cambridge consultants, and they really have accelerated dramatically the FDA and other regulatory processes to bring medical devices to the market. Is that also something applicable to the fiber sensing market? Can you also accelerate that as well, Tom?
In terms of regulatory approvals, in terms of general development, I mean, general development, yes, that's kind of what we specialize in accelerating innovation and development. We've got huge teams of people. We've heard data thrown around a few times. We are very much specialists at handling large data. We have a large team of AI specific for embedded AI engineers to do it, not just standard FPGA work, but embedded AI as well, to handle large data and process large data quickly. So we work very much on accelerating any sort of product innovation. If anybody's interested, please contact me directly and I can give you probably more specific examples at follow-up meetings.
Thanks, Tom. Hey, it looks like Isabel has a question. Tom, how do you deploy those geophones on the completion? Thank you, Isabel, for asking that. Or yes, if she wants to speak, Isabel, if you'd like to speak, totally up to you.
No, please answer.
Thank you, Isabel.
I think they're deployed in a kind of in a string along an umbilical, I believe. But I don't know if that's what you mean.
No, what I meant is that destined to go into the well, into a well, or is it? Yes, I would assume it goes inside the well, because you were talking about signal to noise. So I was wondering, it's deployed behind the tubing or behind the casing, or is it cemented behind the casing, or is it attached to the tubing, or?
I think it's that case. However, I think the design of how it was deployed was actually owned by the client, and we specifically only concentrated on that kind of element.
Okay. Yeah. Right. Sure.
Thank you, Isabel. Thank you. Okay, Tom. Any other questions out there? So, okay. I think just so we keep on time, why don't we go to the next speaker here? I would like to introduce, we have someone here from my actually old home from Quebec. We have Eric Pinet. Thank you for joining us. He's the principal research scientist at Resonance Quebec. And I guess that also, I think your group had purchased FISO just recently, or in 2021. And as you say, I think this is the perfect talk to follow Tom. Because here we're talking about just the specializing in medical integration. So I would like to introduce Eric. Welcome. Bonjour.
Yeah, hello. Thank you. Yes, so I will share the screen.
Thank you for joining us today.
Yeah.
And please, if people have some questions, put them in. We'll make sure that we get the Q&A feature working for the next one, but at this point, we're just going to use the chat. I'll also put my email address into the chat if anybody has any questions or wants to reach out to us at Optica as well. So
do you see my screen?
Perfect. Excellent.
Yeah.
Thank you.
Yeah, so thank you very much, Pamela, for the introduction, and welcome everybody. So today I will talk about fiber optic sensors for medical and industrial harsh applications. So my name is Eric Pinet. I'm Chief Scientist at Physio Technology, which is now Resonetics. So who we are the world leader in the fiber optic point sensing especially. So we are based in the beautiful city of Quebec in Canada, and we design, manufacture, and market fiber optic sensors since almost 30 years now. Late 21, we were acquired by Resonetics, and now we're part of this big family with facilities in the USA, Canada, Costa Rica, Switzerland, and Israel. At Quebec City, we have 4 clean rooms for different types of manufacturing. So we have the MEMS foundry, automated line. We have the prototyping also, and our main market is basically medical, with 80% of our business done there. And for this market, we have the 2 main technologies: the FabriPro and the gallium arsenide. And for the energy and industry, which is 20% of our market, we have the gallium arsenide technology for temperature, and also we have got a distributed temperature sensor with a Raman backscattering. And of course, we are ISO certified. So when we talk about the optical sensors, usually they are used in applications where other sensors fail. I mean, electrical sensors, and usually it's because of the unique advantage of those optical sensors is the fact that they are completely immune to electromagnetic interferences and microwaves. So if you have a high magnetic field, high voltage, or even radiation in your environment, that's the main reason why you should use optical sensor for industrial applications. But also for medical applications, there are other advantages that are very interesting. Of course, the fact that it's intrinsically safe. The sensors will not spark any explosion, but also there will be no electrical contact between the unit and the patient, so it's safe. Also, the nature of the sensor itself on the optical fiber is chemically inert and biocompatible. But what is most important for this technology is the fact that the sensor is very small, and that makes possible to integrate into medical products. So the main technology that we have for medical application is the FabriPro technology. So with a single module, you can integrate different physical parameters such as pressure, temperature, strain, force, displacements, and even refractive index. Our technology is using the white light FabriPro interferometry, which means that we have an absolute measurement of the signal. So you can plug and unplug the system and get the exact same reading. This is a very accurate and a very wide dynamic range for the sensing. Also a very low drift, which is very interesting for many applications. Our technology has a very simple to use with a plug and play. There's a small chip that recognizes the type of sensor and displays the right unit. And also it's very easy to upgrade from the table to the OEM device. And of course, we have almost 30 years now of our sensors and technology in the field, so it's very reliable. For the medical application, essentially, we have optical pressure sensor that are our most sold sensors. We have several diameters from the FOPM IV, which is 0.5 millimeter, down to the FOPM 200, which is the smallest form factor of the market, with a diameter of 200 micron. Those sensors are very accurate with a ±3 millimeter of mercury absolute measurement and very low drift. And of course, we can customize the encapsulation of this sensor to make it suitable for the different application. And actually, it has been used in many approved medical devices already. And what is very important for us is the fact that we have high volume with automated assembly line capability. Presently, we are assembling more than 300,000 units a year, which is quite a lot, and this going up. Now I want to talk about a little bit of some medical applications for those sensors. So obviously for the pressure sensors, the cardiology is one of the most interesting application. So we have some instrumented diagnostic catheters and guide wires where the sensor is measuring directly the blood pressure for evaluation of the FFR, which is a flow fraction reserve, which is basically a number that assesses the severity of a stenosis, and if this number is so it will trigger the use of the placement of a stent to increase the flow through the stenosis. But there are also others applications where we have interventional cardiac catheters. One of the oldest one is the intra-aortic balloon pumping therapy, where we have the sensor placed at the tip of a balloon that inflates and deflates in counter position with the heart in order to bring extra pressure and bring more blood to the heart for surgery recovery, for instance. And so the sensors is used to really trigger to separate between systole and diastole very precisely. And also there are also other catheter like catheter with RF ablation to kill some cells and to prevent some correct some arrhythmia in the heart. The presence of radio frequency makes the use of optical sensor very logical. And in this type of catheter, there are 3 strain sensors that are used in order to have an information about the force applied on the catheter and also the orientation of this force. But there are also other applications, for instance, like skin temperature monitoring and MRI. Here, the very high magnetic field of the MRI station is the reason why optical sensor could be used. Now switching to industrial harsh application. One of the most interesting one is the hotspot monitoring in high power transformer. In this application, we have the gallium arsenide technology who measure the temperature a single point, and those sensors could be placed directly into the winding of the transformer and monitor directly the temperature inside an environment where there is a lot of interferences, and traditional electrical sensor cannot survive there. Another application is regarding the distributed temperature sensor using the Raman backscattering from actually a SensorNet product line that is now built in Quebec City. So here the sensor is simply a single mode fiber that is placed along a pipeline or along a power line to monitor the temperature with a very good spatial resolution down to 1 meter and a good temperature resolution below 0.1 degrees C. And we have also developed some other sensors, single pulse sensors for displacement, where they could be used in a liquid natural gas tank to monitor the displacement of this tank. So here, naturally, you don't want to have a risk for sparking an explosion. So the fact that the sensor is intrinsically safe makes it the right choice. And more recently, we have been selected actually to integrate our displacement sensor into the ITER fusion experimental reactor that is presently built in France in Cadarache. So we are using a Fabry-Perot technology here with a displacement sensor from 40 millimeter up to 280 millimeter range in displacement. And in the ITER fusion reactor, this is maybe the harshest environment you could imagine. You have a very low vacuum. You have temperature from cryogenic up to 200 Celsius for the places where our sensors are used. You've got also a very high magnetic field because of the tokamak design. So the selection of the materials is very tricky. And also, of course, you have some gamma radiation, so you have to select a special fiber to avoid darkening of the fiber, and so that's makes this application very challenging. So That's pretty much what I wanted to talk today. So if you have any question, I'm here to answer your questions.
Thank you very much for a great presentation, Eric. We have met each other before, and I am always so happy to see what progress you have done, not only with manufacturing of the sensor, but also with deployment on harsh environments. This is a meeting for cooperations. Could you share with us a couple of challenges in which the Optica corporate members can help you with?
Actually, for some applications like the ITER fusion reactor, we had some difficulty to find optical fiber that will resist this context. So yes, especially the fiber has to be reinforced by some polymers to make it easy to implement in the field, because of a bare fiber with polyimide coating is not enough. So.
Let me call to the stage FiberCore, FBGS, OFS, all the 5 manufacturers that we have in the room. We are looking for a polymer coated specialty fiber. Could you specify a little bit more what kind of polymer you would like to use for the coating?
For the coating, we have been testing the PEEK coating, but we faced some trouble with the attenuation due to the stress. So macro bending on the fiber make the fiber very prone to signal loss, actually, because the fiber the light is lost when the fiber is bent.
Let me bring to the stage one of the companies who I think can help you, all the way from France, Exail, Matthew Bergont. How can you help?
Yes, so good afternoon, everyone. I was just wondering what type of dose level and dose rates will the fiber experience in your application?
It's 6 mega gray, so it's a pretty high level of your gamma radiation.
Of gamma?
Yes.
Okay, all right. Yeah, it's fairly high, but it's something that we fairly often see in nuclear environments. Yeah. So yeah, okay, we can keep in touch offline. We regularly have fiber in this type of environment on the mega gray level.
Yeah. So thank you.
There are ways to go around this. Let me bring to the stage another company all the way from Lausanne, Switzerland. Kan Yao is representing Ligentech. Kan, how could you help? Kan Yao? Just unmute your microphone. Don't be shy. Tell us how you can help. Well, Kan is wondering, instead of using fiber, could you consider using a very low loss photonic integrated circuit?
Hi, I'm sorry. Yes, so I think because just now Eric, he mentioned that the bending loss is a problem. So in fibers, the bending has to be like several centimeters at least. But if he uses photonic integrated circuits, I don't know, this can realize very compact structures and has a kind of lossless bending loss. So I wonder whether we can integrate fibers and photonic circuits together to get more compact fiber sensors in biology applications. Yeah.
Let's answer that later, but the question that what Ligentech proposes here, Eric, is instead of using the fiber with long bending radius to try to shorten the bending radius by using a photonic integrated circuit. But I think that will incorporate other challenges. But thank you very much, Cam, for being here. And let's continue the room. There's going to be people contacting you offline about the fiber. Already 3 of them have told me that they will be doing that. So there will be people contacting you about the fiber, and we continue with the program. Thank you so much, Eric, once again. We continue with the program, and we go now to one of the key companies in Optica that is bringing value to our members in the field of fiber sensing. It's a company that has been for many years investing heavily on this. It's of course Luna Innovations. Greg Stratton, VP Product Management, thank you very much for being with us. The floor and the attention of everyone goes to the moon, goes to Luna.
Thank you. Hello, everybody. Let me just get my screen up here, and then I would like to tell you a little bit about Luna Innovation. So hopefully you can see that okay. Please let me know if there's any issues. So yeah, Luna is, what I want to talk about today is a little bit more of a broad overview about how our fiber optic sensing technology in both measurement and monitoring applications as we see growth and development in market applications to take advantage of the capabilities of fiber optic sensing. So just quickly here, a little bit about Luna. We've been at this since about 1990. You can find us on the NASDAQ. We're a publicly traded company under the ticker symbol Luna. We've grown over the years through acquisition. Many of you probably are aware of some of the key technologies that we've brought into the company through the acquisition of Micron Optics back in 2018, OptiSense, and then most recently LEOS Sensing in 2022. And our business is really, we're a global company. We've got a worldwide footprint with about 14 locations and about 400 people or so, just to give you sort of an idea of the scope of the business today. We're organized really in two primary categories. We go to market with our photonics test and control business, where we take advantage of some of our OFDR capabilities for test and measurement of optical components, silicon photonic chips, to really enable companies working in that space developing those technologies. And then we also have a number of components and modules and lasers that we supply as an OEM supplier to a number of companies manufacturing their own systems. The other part of our business is what we'll call our sensing and NDT, our fiber optic sensing business. And that's primarily, what I'm here to talk about today. I'm the vice president of product management for that. And we focus our really efforts on sort of three key markets, and that being infrastructure, energy, and industrial applications, where we can really realize the full value proposition of fiber optic sensing. So I think everyone here is pretty up to speed on the physics of fiber optic sensing, so I won't spend a great deal of time here. But I just emphasize that, within Luna, we're really relying on the natural scattering that occurs along the length of the optical fiber. So the fiber is the sensor. This could be deployed in many number of ways, whether it's a polyimide coated fiber that's embedded deposits, as we discussed earlier, or packaged in a cable that could be deployed in an oil well, for example, or the bottom of the ocean. So we've experienced a number of applications throughout our history there, and really with our interrogation schemes and the laser technologies, we're able to probe the fiber and really look for Rayleigh scattering, Raman scattering, and Brillouin scattering. So we sort of have a unique position to be able to take advantage of all three of those effects that happen within the sensor. And it gives us the opportunity to do continuous measurements of strain and temperature. And our technology has the capability of ranging at 100 kilometers with some of our distributed acoustics and then distributed strain and temperature using Brillouin scattering. And and we can also spatially discriminate the measurement as close as 1 millimeter, with our high OFD technology. I'll show you a couple of slides of how this plays out in Luna's technology. So this is a video that's playing that, on the right-hand side here, you can see this is using what we call our high definition fiber optic sensing solution. This is an OFDR scheme that's using Rayleigh scattering in a standard single mode optical fiber. And in this case, we've just set up a ventilation opening here. There's a single optical fiber. It's a polyimide coated fiber that just goes back and forth across this opening. And you can see here in the video, there's a person just moving a heat gun over that sensor, and we're acquiring that temperature data. We're scanning the laser at a rate of about 250 hertz, and we're measuring about every 0.65 millimeters along the length of the fiber, so that we can give sort of a real-time three-dimensional visualization of what's happening with the temperature gradient along that ventilation opening. And of course, we do plot that on a 2D system where we have temperature on the y-axis and the length of the sensor on the x-axis. We're doing the same thing in the bottom set here with strain. In this case, this is a composite fender that has a fiber optic sensor that's bonded to the surface of the fender. This is, you can see the connector here at the bottom of the picture. I don't know how big that's coming up on your screen, but this is a 5 meter long fiber optic sensor that is serpentined back and forth horizontally across this part. And you can see that there's some complex curvature here. There's compound radii and surfaces that would be really otherwise very difficult to instrument with traditional electrical gauges. And again, as we apply a load to this, this is a very small load. We're just squeezing this by hand, but we can pick up signals down to resolutions of around a tenth of a microstrain with this system. And again, along the length of the fiber at every 0.65 millimeters. So we are able to measure through plus or minus 15,000 microstrain with this. And we can actually do this up to 100 meter long sensor with this technology. So it really opens up some unique applications for taking measurements as part of a research program for material development or process development is where we see a lot of our customers using this. Another just quick example will show you sort of how our distributed acoustic technology is used. This is based on a coherent relay system that gives us a quantitative DAS signal. So we're actually measuring acoustic strain here, and we can pick up in a quantitative fashion what's happening on the fiber. And this just shows how we're able to detect the axles or the wheels of a train as it's passing by in real time. And of course, this technology is useful in a number of applications for seismic monitoring, for measuring strain in downhole applications, as well as leak detection in pipelines, and just a number of use cases. But I thought this was a really good illustration of how this worked, and wanted to show that. A third video that is kind of interesting that really illustrates some of the value of fiber optic sensing. We built this Jacob's ladder demonstration, which is something that we probably all school science class, where we have a couple of electric poles, and we apply a high voltage to those, and we can separate them by an insulator and use the electric field to create a traveling arc. So as this plays, you can see the traveling arc here. So what we did is we took a fiber optic sensor, and it's a strand of polyimide coated fiber that's bonded to the outside of this pole. And as the arc goes by, we're actually able to, we're plotting this on 4 separate channels here, but this is one single fiber. But you can see that we're able to pick up the response from the sensor. So it's a very sensitive measurement. So we have the ability to resolve down into the noise floor and pick up the change. And it's happening at a rate where you can see in the time series here that there's the amount of time that it takes for the arc to travel between sensor 1 and sensor 2, for example, is offset here, which is kind of illustrated by this red line. So just another really neat example of how fiber optics can be useful in applications where you have a high EMI field, where conventional sensors are not as well suited, like batteries, transformers, I think were mentioned in power generation facilities. There's a number of use cases there. So some typical applications, that Luna has been involved in through the years really come down to sort of measurement applications and monitoring applications. And I think it's been talked about how fiber optics are really useful for FEA model verification. That's a place where the high resolution OFDR technique is useful. Certainly in industrial processes and manufacturing, process characterization and control, material joining processes, batteries and electrification and vehicles and energy storage. These are some spaces. I don't have time to talk through all of these markets, but these are some spaces that we've seen some typical applications in through the years. And I think as we go forward, what we are doing is partnering to deliver targeted solutions to these markets. So we're excited about the opportunities that we're seeing in these various market segments because of the value of fiber optic sensing that I think all of us get to participate in. And we've been able to deploy thousands of these throughout the last several years. Luna's got a really solid team of people with a lot of hands-on experience too, and we'd love to work with you all and hear from you all as far as how we can help you as well. So that's the end of my presentation. I'd love to hear from you guys. My contact information is here, so feel free to reach out.
Thank you very much, Craig, for a great presentation. There is a couple of questions in the chat. The first one is coming from Joel Villatoro. Joel, please tell us what brings you to this meeting and what do you have in mind? Joel? We lost Joel, so I'm going to read his question.
Yeah, I'm here.
He is.
I'm sorry.
You got to be fast. Alert, please tell us what's in your mind.
Quite interesting talk. And my question is, what parameters do you monitor in batteries and why?
Yeah, good question. So we use our high resolution or our high definition temperature monitoring capability. So since we can look all along the length of the fiber at 0.65 millimeter spatial resolution, you can take a large battery pack that has thousands of cells, for example, and you're able to place the fiber, between the cells, along the cell gradients. You're able to validate the cooling design of the battery pack. And really the goal is to identify any conditions that exist. And it could be something as simple as a bad contact that can create heat in the battery pack that could ultimately lead to a thermal runaway condition. So using the fiber optic sensing technique, we're able to really look at that in detail and identify during charging and discharge cycles any condition that could exist that could result in a catastrophic failure of the battery that could be unsafe, really. So that's the primary reason. And since it's completely immune to the electric field, it's purely passive, there's really no risk of shock or anything like that to the user.
Thank you.
Hope that answered your question. Yeah.
Thank you very much, Joel, and thank you for being at the meeting today. It is great. Pamela, what else do we have on the table?
Okay, we also have, let's see, we have from Deep Light. Are you there, Andre?
Yes. Hello, thank you for the presentation. I have a question. Do you use any lasers with chirped pulses, so frequency modulated lasers in your schemes, and what lasers you're using usually?
Yeah, good question. So between the techniques, we use different lasers. In our OFDR, we use a tunable laser that we scan through different wavelength ranges depending upon our measurement range that we need. We do some external modulation on some of our other lasers in different setups that we have as well.
Andre, I'm such a huge fan. You need to tell me, because we met at Photonics West and we talked quickly about the laser that you are bringing to the market. Could you specify, because Craig, listen to this. This is huge. Andre, could you specify a bit what laser you're bringing to the market?
Yeah, so we are developing photonic chip-based laser system, and in butterfly package, standard butterfly package, we have fiber frequency noise of fiber laser. So it's even lower than fiber laser. It's based on waveguide spiral cavity. And what is important, in addition to ultra low phase noise of the laser, we have chirp capability. So custom has direct access to laser frequency in bandwidths up to 10 megahertz. So it's much faster than usual micro heaters, which are used in photonic chips.
Craig, this is one of the ones to watch. I am really, really rooting for these guys. Andre, thank you very much for being with us. Pamela, what else do we have on the table?
Okay, let's Kezaban, I'm sorry, from CERN. Can you have, looks like you have a question as well. It's good to see.
Yes, I have a question regarding the optical fiber sensor you are using with the Odyssey interrogator. Is it possible to use only standard optical fibers or also thin optical fiber like 80 micrometer or 4 micrometer cladding diameter?
Yeah, great question. So we have some direct experience with 80 micron fiber and embedding that in composites, and that does work fine. as the cladding goes down, really what we're looking at is the backscattering threshold of Rayleigh scattering in the fiber. I haven't tested 40 micron, so I don't know what the scattering coefficients would be, but it would certainly be something that would be fun to look at.
Okay, thank you.
Okay, thank you for asking that question, Craig. Thank you so much, and thank you for joining us today. This has been a really impressive day and an impressive meeting. This has really shown the importance of the optical fiber sensors, from everything from medical diagnostics and treatments to the oil and gas exploration to space exploration, as well as exploration and navigation of our world's oceans. So this is, pretty amazing to see the full extent of where we are needing all this. And as an avid sailor, I am really looking forward to hearing from our next speaker and our last speaker, and I would like to thank everybody today. So our next speaker is Romain Guillard, joining us from Brittany, France. He's a fiber optic sensor engineer at Pixel-sur-Mer, very well known for the navigation and all of the scientific for getting our amazing World Cup and all the other, I think one of the oldest international competitions in the world, I think. And so it's just a real honor to have you joining us today to talk about something very cool and very interesting. Not everything is so cool, as I say, from medical diagnostics to racing these massively huge boats across the water. So please, over to you, Romain. Merci beaucoup.
Thank you for this introduction, and good morning or good afternoon. It depends on your location. Can you see my screen? It's okay for you?
Yes.
Okay, perfect. Okay, so I'm Romain Guillard, and I work as a fiber optic sensors engineer at Pixel-sur-Mer. And today I'm going to show you our fiber optic sensing application applied essentially on racing sailboats. Just firstly, I will introduce briefly my company. We are located in France, in Brittany. Pixel-sur-Mer is a quite small company with 25 employees. We work mainly in France, but frequently we can go abroad to work in the different countries in Europe or sometimes as far as New Zealand. So we have 3 business units. The first one is integration. The goal of this business unit is to supply and to install electronic device on different kind of sailboats. It could be batteries for power supply, computer, or antenna, and so on and so on. And the second business unit is our design office. We have a team of engineers who works on flight control system and flight control algorithm, and they develop our homemade product as well. And later during my presentation, I will speak more about the Exocet Blue. It's our data logger. It's very practical for our installation because we can record different data from different kind of sensors, and we can synchronize together this data. It's very practical to carry out data processing with it. So we equip different class of boats for the America's Cup, the big one, the big trimaran, the class Ultims. So every kind of boats has its own features, but all of them sail on very harsh environment. That's why it's very essential to install the fiber optic sensors on the structure safely, and at the end the installation has to be very strong. why do we put fiber optic sensors on boats, and which elements are equipped with them? So we can put the fiber optic sensors on the masts for two reasons. The first one is to have an alarm system, because the mast is the mast is frequently under stress because it supports sails, and so sometimes if wind is too strong, it's possible the mast can be broken apart. So to avoid this, it's very essential to measure strain locally along the structure, and check in a real time what is the value, and if the value is too close to the limit of the structure, we can set a few alarms just to warn the crew, and the crew has to act in consequence to avoid the failure. Or we can have a more complex application. We can use the strain data as input parameter of a 3D shape sensing algorithm, and it's possible in this case to rebuild the shape of the mast, and the shape. Knowing the shape of the mast is very essential, because the shape of the masts, but the profile of the mast affects the shape of the sail, and the shape of the sail has a big consequence on the speed of the boat. We can put as well fiber optic sensor on the hull for two reasons. The first one is the numerical design tool of the hull are based on a few assumptions, but these assumptions is the expected load cases during the future sailing. So it's possible to equip a first generation of hull. After it's possible to sail with this version of the hull, pick up strain on the structure during sailing, and then carrying out data processing to know which part of the hull is vulnerable, where are the impacts of the wave against the hull, and statistically we can know which part of the hull need to be reinforced, and which part of the hull can be lighter, and so we can reduce the weight of the structure at the final at the end. And so we can install fiber optic sensors on the forearm. This element is very essential because it enables the boat to fly over the water. So we can put a sensor to warn the crew if something wrong will happen, yeah, like a failure. Or we can put a sensor to know how is the mechanical behavior of the structure inside the water, and like this we can get information, and for the next generation of the forearm, it's possible to improve it to make it more efficient. So we use optical fiber, but why? Because it's highly compact. The diameter of the optical fiber is very similar to the diameter of human hair. It's very suitable for harsh environments, especially in marine environments, because optical fiber is made are made of silica glass, and there is no corrosion. It's very accurate. We can get the strain very precisely, and we can put them in a series. On the picture, you can see, for instance, in aeronautics, it's very frequent to have a resistive strain gauge. It's very reliable. Sometimes it's shipped, but the issue is it's not possible to put them in a series. You need to wire a lot of cable to connect everything together. So with the optical fiber, it's you can have less cables. It's a lighter installation, and there are several fiber optic technologies, but we use FBG, fiber bright gratings, with wavelength division multiplexing, because we have a few requirements to meet. Especially, we need to know perfectly where is the strain, where the strain measurement was done, and we needed to have interrogator unit which can be put on board on the sales boat. Fiber bright grating. I will explain you very quickly how it works. It's a conventional. It's a conventional optical fiber, and at a specific location along the optical fiber, we change the properties of the material inside the optical fiber by using a very powerful or high intensity laser. After the manufacturing process, we get a grating within the core of the optical fiber over a 5 millimeters long section. This grating is very similar to a series of a mirror, but every mirror has a very low reflectivity, and when sunlight it's launching at the input of the optical fiber, a small amount of the intensity of light is reflected back. And if we analyze the reflected spectrum, we can note a peak, and this peak is centered around a specific wavelength, which is the bright wavelengths. And the value depends on the material of depends on the refractive index of the optical fiber, and it depends on the pitch of the grating. The pitch is the distance between the mirrors. So if we change the features of the grating by putting it under tension or by increasing the temperature, you will shift the wavelength. So for the implementation, we have two solutions. We can put the optical fiber inside the material composite during the lamination process, or it's possible to bond it on the surface. And when the structure gets loaded, for instance, for the masts, if the masts get bent, the optical fiber is strained as well, because it's bonded on the structure, and we can note a wavelength shift. And by measuring the wavelength shift in real time, and by using a calibration law, it's possible to deduce the strain of the optical fiber, and the strain of the optical fiber, it's the same as the strain of the structure. We can use several fiber bright grating by doing a wavelength division multiplexing. Every grating has its own wavelength. But there is a problem. It's very easy to measure strain. You can get a value, but the most difficult thing is to find the context of the measure, and especially for boats, strain will be depend how was the sea during sailing, how was the angle of the boat on the surface of water, how was the speed of winds and direction, and so on. And to know the context, it's very essential to measure several data at the same time. That's why we use our data recorder, and we can plug onto the interrogator. Like this, we can record the strain from fiber optic sensors, but we can plug as well other sensors like GPS antenna to know the location of the boat, or inertial unit to know the angle of the boat. We can record together, we can synchronize, and this device, the Exocet Blue, has a web interface. It's quite easy to configure. You don't need to be an expert in computing program, and you can set a few alarms, and we can visualize in a real time the strain of your structure by doing a few dashboards. And it's possible to access the data remotely with a cloud service.
Very, very interesting. And you had really
It's my
showed
last
the
slide.
purpose.
It's
Yes, tell us,
the last one. Sorry. And for the future, okay, we use mainly essentially a LUNAS interrogator. It's very practical because the spectrum width is very wide, so we can put a lot of sensor on our installation. But sometimes we need a more compact solution with a low electrical consumption. That's why we prospect other interrogators, sometimes based on silicon photonics technologies. We need connectors, especially heat-resistant connectors. And about temperature sensing, we work on a research project. The name it's called Kafka, and the goal is to use a multi-core fiber to measure a temperature inside composite materials, and to finish. Sometimes very frequently we carry out a multi-directional strain. So we need to put the sensor with a different angle on the structure. But I think it's a good idea to develop a solution more compact. Maybe it's possible to have a writing within a see-through patch. But,
thank you so much, Romain, and thank you for all these challenges. Those mean the world to us. We need to address a couple of the challenges. The contact details for Romain are there, but Romain, wait for us because we have a few questions for you. The first one is coming all the way from the European Space Agency. Ian Mackenzie, what do you have in mind? Ian asked, sorry, Ian, are you with us? He asked me, how do you manage cross-sensitivity of strain and temperature in embedded sensors?
Yeah, it's quite critical because if you want to manage that, you need to put one FPG inside a tube. But the problem, tube is quite wide. The diameter is roughly 600 micrometers. And it can affect the structure of the composite materials. But
the second question, go ahead.
Yeah, and that's why in the future we work on a multi-core optical fiber, and with this solution, it will be possible to put directly the optical fiber inside the composite material, and it will be possible to measure at a specific location, strain and temperature separately.
Multicore fiber for shape sensing. Bram, what do you have to say about that?
Yes, I was also going to add, first of all, thank you, Romain, for the interesting talk. And we have been in contact lately, so it's good to see you here as well.
Thank you.
Indeed, when it comes to shape sensing, using multicore fibers, is of course also an interesting way of doing it, because then you can use the differential strain response to calculate curvature and shape directly without being dependent on the way the fiber is installed. So this could be an elegant way forward, but I already saw in your last slide that you're working on that. So it would make sense to also connect on this topic as well, because we have a basically turnkey solution for shape sensing based on multicore fiber and the inscription of WDM arrays in multicore fibers. So happy to talk on that as well.
Okay.
You all have to connect. We have to say goodbye to our YouTubers now, so allow me to do that. Just remember that you want to get in touch with any of the participants today. All these people came to the meeting looking for partnerships. If you want to get in touch with any of them, all you have to do is drop me a line, drop me an email, jpost@optica.org, and I will be more than happy to facilitate the introduction. Remember, if you're looking for market reports, where do you go? Where do you go for market reports? Optica.org/market reports. Go there. We have put all of them there. Select what you want, put your email, they come to your mailbox. Thank you very much, everyone, for making fiber sensing an interesting, very interesting